All right, welcome to class for Monday, April 20th. Today we're going to be talking a little bit more about angular acceleration and moving in circles, which seems oddly appropriate for this phase of life. Reminders. This week, the Wiley Plus homework is chapter 10. There's a homework assignment and an adaptive practice. There's a perusal reading due Wednesday on torque. So sometime today or tomorrow, hop onto perusal, do some reading, leave some comments. Video experiments. So video experiment number 6 was posted last week. Number 7 will be posted today. They're both on angular acceleration, rotational kinetic energy, those sorts of things. And then the other thing to remind you of is that the final exam will be oral, and you need to schedule a time during finals week to meet with me over Zoom. You'll do that using a doodle poll. So I sent the doodle poll out again this morning via email. I think as of right now, let's see. Looks like as of right now, come on, load. 9 of you have done that. So thank you if you have. If you haven't, sign up soon. There are plenty of time slots. There are more slots than there are people in the class, but you know, the desirable spots, I guess, are going fast. You'll also notice that there are half-hour time slots on the doodle poll. These won't take a half hour. I'm going to cap them at 20 minutes. That just gives me time to finish with one, before I have to get started with the next. All right. Questions about any of that stuff? All right, then we'll jump in and talk about physics. Okay, so here's your polling question. And yes, I know if you actually tried to spin these gears, they wouldn't work because the teeth don't interlock properly, but ignore that for a minute. We've got 2 gears as shown below. They're gonna work like gears, so they move together, right? They don't slip on each other at all. So you have a point on the edge of gear A that travels a distance of 1 meter. How far does a point on the edge of gear B travel in that same time? So let me start up the poll. All right, I'll give you another 10 seconds. Going once, twice, sold. All right, we had almost an exactly 50-50 split between C and D. So Somebody who said C, defend your answer.
If you're just talking about a point on the edge of the gear, then it's just going to be a 1-to-1 ratio between the gears. If you're talking about number of rotations, then that's when the size of the gear matters. But because the gears theoretically interlock, that's why I said if one moves 1 meter, then the other one will too.
Okay. Anybody want to get to argue D? Nobody likes D anymore, huh? Well, Davey was very convincing. All right. He's actually right. The answer here is C. So the thing to remember is if they're not slipping with one to another, right? The gears aren't slipping. Then each point as it goes by, right, moves the same distance in the same amount of time, right? So the distance that a point moves around the edge of the gear is going to be the same. Now, this leads us to the follow-up question. Same two gears. Now we're going to have a point on the edge of gear A that rotates through an angle of 1 radian. Over what angle does a point on the edge of gear B rotate? So let me relaunch the poll here. Okay, can you see the poll?
Yes.
Great. All right, I'll give you another 10 seconds. All right, going once, going twice. Sold. Okay, most people here said D. Most people are right. The answer is D. And the reason for that is that if gear A rotates through an angle of 1 radian, right, that means that a point on the edge of gear A traveled 1 meter. Okay. The point on the edge of gear B also traveled 1 meter. And as we just showed in the last one, right, because they don't slip, which means anytime gear A moves, the point on the edge of gear A has to travel the same distance as the point on the edge of gear B. But 1 meter is 2 radians for gear B because gear B's radius is only half a meter. So, the gears, what they do is they change the angular variables, right? They don't change the linear ones, they change the angular ones. Okay, third question in the set. We've got same two gears. Gear A has an angular velocity of 1 radian per second. How fast is gear B rotating? I'm going to relaunch the poll. All right, can you see it?
Yeah.
All right, I'll give you another 10 seconds. Going once, going twice. Sold. All right, this one's interesting. Let me share the results here. So as you can see, we actually had a whole variety of choices here. E was the slight favorite. Okay, somebody want to defend E? Oh, come on, E people. Tell us the glories of E. Oh, come on. I know 4 of you voted for E. 4 very bashful people. We need like hold music. Our call will be answered as soon as possible. All right, come on, E people. Give me an answer. What do you got? Why is it 4 radians per second? All right, our E people are definitely not very confident in their responses, or, you know, are asleep. Okay, anybody else want to defend A, B, or C? Well, the right answer is D. So good job, D people. So this is exactly the same as the last problem, right? In 1 second, gear A will go through 1 radian, okay? If gear A goes through 1 radian, it means a point on the edge goes through a distance of 1 meter. So the point on the edge of B also goes through a distance of 1 meter, which is 2 radians. That all happened in 1 second. So the angular velocity here is 2 radians per second. So what gears do is they allow you to change the angular variables. They don't change the linear variables, right? So in this case, a point on the edge of gear A is moving at 1 meter per second. That's also going to be true for a point on the edge of gear B. It's also going to be moving at 1 meter per second. The trick is that gear B, 1 meter goes a lot further around gear B than it does gear A. So gears allow you to change an interface between gears allows you to change the angular variables, right? It allows you to change the angle something goes through, the angular velocity. And that's what you see when you look in machinery that has gears. What it's really trying to do is change the angular velocity, right? Or the angle it goes through, or the angular acceleration. If I wanted to change the linear velocity, how would I do that? I want to change the linear velocity of a point on the edge of something moving in a circle. How would I change it? Because we just said gears won't do it. So how would I do it? Oh, go ahead.
You have to increase the angular velocity.
Right. We'd have to do something. We could do that, right? We could just spin the whole thing faster. But what if I didn't want to increase the angular velocity, say, of gear A? I just wanted something moving faster than 1 meter per second. How would I do it?
Increase the radius.
Yeah, I just make a bigger radius, right? This is why you'll see in assemblies that have a lot of gears, you'll see two gears stacked, like here's one gear spinning around this way, and then it'll be connected to a little rod, and then it'll have another gear spinning around the same way. And that smaller gear, the edge of that smaller gear, will be moving slower in linear velocity than the edge of the bigger gear. And of course, you could switch the sizes. So the concept I want you to think about here is what happens when two objects move without slipping relative to one another, right? Okay, so we'll use this later when we start talking about work, doing work with angular things, okay? Okay, so let's talk a little bit about moving in circles. So let's suppose, I'll stop sharing my poll here. So last week we talked about what happens if you accelerate something, and do an angular acceleration, right? So you move something in a circle, like a wheel, right? Or some kind of spinning object, and you make it so it spins faster or slower. Okay, so you change the angular velocity. So that if we're talking about something moving in a circle, we can actually make it accelerate in two different ways. And I've got those drawn here on this little diagram. Okay, we can make, if we imagine that this is a object moving in a circle, right? And we want it to speed up its rotation rate, we have to do two different things at the same time. We're going to have a centripetal acceleration that keeps it moving towards the center of the circle, right? So it moves in a circle. And we're going to have a tangential acceleration that makes it move faster around the circle, hence increases its angular velocity. So we've got to do both in order to make the thing spin faster. Okay.
Oh,
Okay, I think I'm back. Am I back?
yeah,
Great. All right, where did you lose me?
okay.
Or where did I lose you? I believe I was babbling about something. Did I lose you again?
I'm not too sure. It sounded kind of too robotic to tell because of the internet.
All right. So did we finish the explanation on the gears? Is everybody good with the gears?
Yes.
Okay. Let's talk about things moving in circles again, which seems very appropriate. Okay, so we learned earlier in the semester that if you want something to move in a circle, you have to accelerate it towards the center of the circle, right? We call that a centripetal acceleration, an acceleration towards the center. If we want something to go in a circle faster, we also have to accelerate it tangential to the circle, right? So that's what's diagrammed here. We've got some particle moving in a circle, right? And that requires an acceleration both towards the center of the circle to keep it moving in a circle, and an acceleration along the circle, right? Tangential to the circle, that will increase the velocity of the object, right? Make it go faster around the circle. So here's the question: which one of these two causes an angular acceleration?
The tangential acceleration.
The tangential one does it. Why not the centripetal?
That one just keeps it going in a circle at
Right.
the same speed.
Because if we remember our acceleration, our formula, right, used a cross product, right? We had the tangential acceleration, right? The acceleration, the linear acceleration was equal to the cross product of radius and the angular acceleration, okay? And if our acceleration, right, our centripetal acceleration is in the same direction as our radius, actually it's the exact opposite, but there's no way to make a cross product because a cross product gives you a vector that's perpendicular to both of the other two vectors, okay? So there's no way to do a cross product between the radius vector, right, which goes, let's see if I can draw this. The radius vector, which goes like, right, here's the center, goes like that, right? There's no way to make a cross product of that with any other vector that will point back towards the center. Now, there is a way to make a cross product with this radius vector that will point this way. Let me use a different color. No, not that one. There is a way for us to make a vector that will point that way. And we can use the right-hand rule to figure it out, okay? So we need our, if we use our right hand, right, we're accelerating around the circle counterclockwise, right? So take your right hand, curl your fingers counterclockwise. Which way does your thumb point? Come on, which way does your thumb point? Did I lose everybody again?
No.
Okay, so again, how do we do this? We take we want to take our hand, right hand, okay? You know that you want to curl your fingers around the circle the way you're traveling, right? So if our acceleration is counterclockwise, looking at the screen, we need our fingers to rotate counterclockwise, right?
Thumbs pointing outward, like towards
Thumbs
us.
pointing outwards. So the thumb is pointing out of the computer screen, right? Okay, so we need, are all three of those vectors perpendicular to each other? Yeah, because your radius and your tangent to a circle are perpendicular to each other, right? And your thumb is pointing out of the computer screen. Both of those other vectors are in the plane of the computer screen. So you've got three vectors that are all perpendicular to each other. So hence, you've got a cross product. So when we talk about the angular acceleration only is going to affect or be affected, or affect, depending on which way you think about it, the tangential component of the acceleration. Now, what about the centripetal component of the acceleration? Where does that come from? The tangential component is related to how fast you're moving around the circle, right? The centripetal component just comes from the fact that something's making you move in a circle, whether it's gravity or, you're on a track, or a string or whatever. It's something making you move in a circle, okay? So we have both things going on here. We have a centripetal acceleration and we have a tangential acceleration, okay? So let's take a look at these. Here's our sample problem. Nope, I'm just leaving little arrows all over the screen. All right, there we go. Sample problem. Okay, you've got a skateboarder and we're on top of a quarter pipe, which is just a quarter of a circle. The circle has a radius of 3 meters, okay? We want to find the tangential acceleration that the skateboarder experiences as a function of angle. Okay, how could we do that? If I want the tangential component. Oh, by the way, let me, hold on one sec. I'm going to drop the link to these slides in the chat, maybe, if my internet doesn't die. Okay, there's the link to the slides. Hopefully you can still hear me. And we're going to come over here and stop sharing our screen. And I'm going to come over to our webcam. Okay, so we've got our quarter pipe, which is really just a quarter of a circle, right? So here's our circle, right? And we're going to do a quarter of it. So we're going to go from here down to here, okay? And we know that the circle has radius r, and r is 3 meters. Okay. What if I drew a free body diagram of the skateboarder right here? What would it look like? Did I lose everybody? Oh, come on.
But
Okay, nope, still here.
and my press to talk button wasn't working. But so could you repeat the question?
Yeah, so what's the free body diagram for this skateboarder look like right there on the side, right as he's dropping into the quarter pipe? What forces are acting on him?
Gravity, right?
Gravity. Anything else?
Normal force.
There's actually, in this case, there's not a normal force because there's nothing pushing him into the wall for the split second he's headed straight down. Right now, there's gonna be a normal force as soon as you move away from that spot, right? Because if there wasn't, he'd just drop. But eventually, he drops a little bit, hits the pipe, and the pipe starts pushing him around. Okay, what does the free body diagram look like at the bottom? Well, it's still got gravity, right? My pen just died. Oh, man. Nothing's working today. All right, we're doing it all in red. We've still got gravity at the bottom. What else do we have?
Normal.
Now we've got a normal force, right? Okay, so if I pick a spot in the middle here, what's going to happen? What does that free body diagram look like?
We have some gravity and some normal force.
Yep, we've still got gravity. And now we've got normal force going off in some other direction, right? So the component, so when we do this, right, what we want to do is break this vector up each time into a tangential component and a radial component or a centripetal component. That centripetal just means pointed towards the center, right? So each time, so what we want to do here is think about at each time how much of this acceleration is, or how much of these forces are tangential and how much of them are radial. Okay, so here, how much of gravity is tangential to the circle?
All of it.
Right. What was that?
All of it.
All of it, right? So, and how about here? How much is tangential to the circle?
About half.
Well, some of it, right? We could draw the components out like this and this, okay? And here, none of it is. So we need something that starts off at all of it and then decreases until you get to none of it over here. So that means our tangential component of force has got to be equal to mg, right? Because it's gravity, times something, some function that's going to go right here, that's going to be a function of angle. What's the function that goes here?
Is it cosine?
Cosine might do it, right? If I put cosine in here, that'll give me 0. I'm sorry, that'll give me 1 up here, right? And then it'll give me 0 right there, right? At pi over 2. So in fact, you're right. The function of the force is just going to be mg cosine theta, which means that the tangential component of the acceleration is just g cosine theta. Okay, so we've got it, right? The thing was asking us, what's the tangential acceleration that the skateboarder experiences as a function of angle? And the answer is that, right? It's just g cosine theta. Great. Okay. Now let's do the follow-up question here. So if I come back and share my screen, am I still cutting out for people?
No, well, not for me.
No, I think it's just a like occasional sputter, I guess, in how Wi-Fi is.
Okay. Well, we're just going to plow ahead and hope for the best. All right, so here's the follow-up, the second part of this question. Now we want to find the centripetal acceleration that the skateboarder experiences as a function of angle. Okay? So we already figured out the tangential component of the acceleration. Now we want to figure out the centripetal component or the radial component of the acceleration that they experience. Okay? So if I stop sharing my screen and come back over to the paper here, right? So what's the formula for centripetal acceleration? If something's moving in a circle, how much acceleration does it need? All right, help me out here. Moving in a circle. You're moving in a circle at some velocity.
Is it v squared over r?
Yeah, there you go. It's your velocity squared, your tangential velocity squared, divided by the radius of your circle. Okay? Which means that our centripetal acceleration, right? We need to know how fast you're going. Now, how fast are you going up here? When you first drop into the quarter pipe.
You're not.
You're not, right? So up here, your velocity is 0. What about down here? Velocity is obviously not 0, right?
It would be at its maximum.
Right. Then it would start decreasing again as you went around. Okay. So how could we figure out what your velocity was as a function of angle, right? Because if we knew what your velocity was as a function of angle, we'd have our centripetal acceleration, right? We just plug it into there and we'd be done. So how do we know what our velocity is as a function of angle? If I wanted your velocity as a function of time, we'd want to do this with Newton's second law. But I don't want it with time. I want to know the relationship between velocity and position. So what's the way we relate velocity and position?
Kinematics?
We could do so that's what we do, right? If we wanted to do this with Newton's second law, right, we could. We just have to figure out what your velocity is, right, from finding all your forces and adding them up and doing your acceleration. Problem is, we don't actually know what our normal force is, right? Our normal force is whatever it needs to be. So how could we do this problem in a way that we don't have to deal with this pesky normal force? Maybe another way to say this is, what doesn't the normal force do here? Normal force is always perpendicular to the circle, right? It's always perpendicular to the direction you're moving. So forces that are perpendicular to the direction of motion can't do any what?
Work?
Work. Can't do any work, which means this is a conservation of energy problem. We can say, okay, what energy did you have up here? What energy did you have down here? And we can relate the two, okay? So at the top, what energy did we have at the top?
Potential energy.
Yep, no kinetic, right? But we had potential energy. So let's say we had our kinetic energy was 0 and our gravitational potential energy was, because this height is r, would just be mgr. Okay, now let's think about, instead of thinking about the bottom, let's think about this in the middle, because that's what we really want, right? In the middle, we have some kinetic energy, right? But we still have some potential energy too, right? Because we're not all the way at the bottom yet. So how much potential energy do we have?
Still MGR.
Yeah, well, it's mgh, right? If we can make a little triangle here and figure out how much, right? So if we make our triangle here, we know that this whole side is r, and that this is r, and this is our h, right? So we have mgh. Okay, how do I relate H and R and our angle, right? Here's our angle theta, which means this is also our angle theta. Now it's just a trigonometry game, right? I know that this piece from here to here has got to be R sine theta, right? Because there's theta. Here's the hypotenuse is R. So this piece, the opposite side, has got to be R sine theta. So H is just R minus R sine theta. So that means our gravitational potential energy in the middle is mg R minus R sine theta. Or I could just clean that up as mg R times 1 minus sine theta. Now let's double check that, right? If we put this all the way up at the top, we put theta equals 0, we get that our potential energy is 1 minus the sine of 0, which is 0. So we're good. Our potential energy is the same as what we said it was at the top. How about at the bottom? Well, sine of pi over 2, right, which is 90 degrees, is 1. 1 minus 1 is 0, which means we have no potential energy, all kinetic energy. So we're good. Okay, we'll have to move on to another sheet of paper here because we're out of space. But if I put those things together, I'm going to get my statement of conservation of energy is going to look like mgr is equal to my kinetic, 1/2 mv squared, plus my potential, mgr 1 minus sine theta. And voila, I've got a statement here that relates my velocity to my position. So now all we got to do is solve for v. Now we can make our lives a little easier if we just cancel the m's everywhere, right? We move this term over to the other side. We get gr minus gr times 1 minus sine theta equals 1/2 v squared. And something cute happens here. This is gr minus gr. So this term and this term cancel. And all we're left with is gr sine theta equals 1/2 v squared, which means that our velocity is 2gr sine theta square rooted. Now what do we do? We've got our velocity. Sorry, go ahead.
Do we just plug in what we know?
Yeah. So now we can just take this and plug it into that formula for centripetal acceleration. Our centripetal acceleration is just v squared over r. Well, conveniently, this is a square root. So it just takes away the square root, and we get 2gr sine theta divided by r, which is just 2g sine theta. Okay? And this is our centripetal acceleration. Okay, let's compare these two. Let's see if I can get them both on the same camera screen. Our tangential acceleration is g cosine theta. Our centripetal acceleration is 2g sine theta. Okay? So you can probably guess what I'm going to ask next. If we go back over to the slides here. Now I want the magnitude of the total acceleration that the skateboarder experiences as a function of angle. So now I just need to recognize that my tangential and centripetal components are always perpendicular to each other, right? Because it's a circle. The radius of a circle is always perpendicular to the tangent of the circle. So these two components are perpendicular to each other, which means that now I can come over here and find their magnitude. How do I find the magnitude?
I forget that you need the what is the dot or cross product of the vector?
I don't actually have to do any dot or cross products here. This is even an easier question than that. To do this, all I have to do, right, if I want the magnitude of a vector and I know the components, I just square the components, add them up, and take the square roots. So if I square the components, let me come back over to my document camera here. Maybe. Yep. Oh, there we go. Come back over here to my document camera. My magnitude of my acceleration vector is just the square root of the tangential component squared plus the centripetal component squared, which, if I plug in my values, is the square root of my tangential component squared is just g squared cosine squared theta. My centripetal is 4g squared sine squared theta. Okay, let's plot these things. So let me come over here and share a lovely window that has Desmos. Desmos go. There we go. Okay, so I'm going to plot up three things. I'm going to plot up first my tangential components, right? And I'm going to call everything y because that keeps Desmos from getting confused about what I want on the y-axis and what I want on the x-axis. But this is just my tangential component, which is just 9.8 times the cosine of my angle, which I'm just going to call x. Okay? Now, I need to rezoom this thing because it just assumed something, right? I only want to look at things from 0 to pi over 2, which means I'm going to make this like negative 0.1 to like 1.6. Okay? And then I'm going to have to readjust how I zoom in the y, but I can actually just do that by scrolling, right? So there's our tangential component of acceleration. And it makes sense, right? When you first drop into the quarter pipe, you get a lot of acceleration. But as you go down the quarter pipe, that acceleration drops until eventually when you are at the bottom, you stop accelerating and you actually get negative acceleration, right? If it was a half pipe, right? You'd actually start slowing down as you went up the other side, okay? Okay, there's our tangential components. Now let's put in our centripetal components. Our centripetal component is 2 times 9.8, 9.8 times the sine of our angle, okay? And you can see that something weird has happened here, right? It's way off the screen. So I'm gonna need to rezoom what's happening in the y direction. So let's make the y go to, I know the biggest that it could ever get is twice 9.8. So let's make it go to 20. Okay, and there we go, right? If we look over here, our maximum is at pi over 2, and it gives us a maximum of 19.6 there. And this makes sense, right? Because here, we're not moving at all, so it's not hard to keep us moving in a circle. But as we start picking up speed, it becomes harder and harder and harder to keep the skateboarder moving along that circular path until you get to the bottom where that's the hardest place to be moving in the circular path. Because if you remember, like when we talked about the water in the bucket, right? That was the part that really strained your arm, was the bottom of the circle. Because the force, the normal force, right? The force that was making you move in a circle had to overcome both gravity and the tendency of the thing to want to go in a straight line instead of going in a circle. Okay, so now let's look at what happens when I take the magnitude of that vector, right? Now, the thing to be careful of, these two directions are always changing, right? Which they're always tangent to the circle and the radial direction, but that's actually moving as you go around the circle. But it's okay because they're always perpendicular to each other. So that means my total acceleration is just going to be the square root. So there's my square root of 9.8 squared times cosine squared plus 4 times 9.8 squared times sine squared. And voila, what do I get? I get this nice curve that is all of the acceleration is tangential down here at the top of the ramp, right, at 0 angle. All of it is centripetal at the bottom of the ramp. And in the middle, I get a little of both, right? I get some centripetal acceleration to make me move in a circle because I have some velocity. And I get some tangential acceleration to speed me up. Okay, so does this make sense?
Yes.
This idea that we've got both the centripetal acceleration and the tangential acceleration going here, okay? So now what if I did something weird? What if I did something like, say, I've got a motorized skateboard, or I've got some other thing that is going to change how I do this, right? Well, we could figure that out, right? Because we just have to break the acceleration into components and add the components of that acceleration to each piece, right? We could solve that problem. We could do this any way we wanted. It turns out we could actually do this in any shape we wanted. It doesn't have to be a perfect circle either. The only difference is if it's not a perfect circle, then our radius isn't constant, right? Our radius is going to change, which would make this a little messier. But this idea that we have both things happening at the same time happens a lot. Okay, somebody give me an example. Give me an example of where you have both centripetal acceleration and tangential acceleration on something moving in a circle. And skateboarders are out. Can't use skateboarders. All right, come up with an example for me. Where does this happen?
It was kind of hard to hear you earlier on what you were saying.
Oh, I'm sorry. Apparently my
So I
internet
don't
is
know.
just going to be rough
Well, I don't know.
today.
Maybe others.
I was saying I want an example of when you experience of something that moves in a circle that is experiencing both a centripetal and a tangential acceleration. So give me an example from sort of everyday experience. When does this happen? When does this happen on a car? So what's moving in a circle on a car? Give me an example of something that's moving in a circle on a car.
Wheel.
Wheels. Okay. So the wheels, if the wheels are moving in a circle, there always has to be a centripetal acceleration, right? And in the case of the centripetal acceleration on the wheel, on the edge of the wheels, that the force that's supplying that just comes from the fact that the wheel isn't spinning so fast it flies apart. Anybody ever seen a truck tire blow out on the freeway? That's what happens when the material strength of the tire is not enough to keep the wheel moving in a tight circle, right? And it's kind of spectacular and terrifying if it's in front of you. I once actually had that happen, and I got hit by a piece of the tire. I was close enough to it that a piece of the tread actually hit my windshield. Scared the bejeebers out of me. Okay, so got centripetal acceleration anytime you're moving in a circle, right? So how would you get a tangential acceleration on the edge, on that material on the edge of a tire? What would the car have to be doing to get a tangential acceleration?
Car would have to be accelerated.
Yeah, if the car's speeding up or slowing down, right? If the car's braking, it's going to have a tangential acceleration that is backwards to its velocity, right? And if it's speeding up, it's going to have a tangential acceleration in the same direction as its velocity. Okay, so there's one. There's one where it happens on a car. All right, give me another example. Where does this happen in real life? Okay, can anybody flip pizza dough? Know what I'm talking about? You know, you do the spin thing.
Yeah.
Okay, tell me how that has to do with this. Why do you spin pizza dough?
To make the pie bigger.
Yeah, you're trying to expand the edge. In other words, you have a circular pizza, right? And you want to make the radius of the edge bigger. Okay, so that's going to require what? You spin the thing, right? Why do you spin the thing to make it bigger?
The centripetal force pulls on it.
Yeah,
Pulls
because
on-
if you've got a centripetal acceleration, right? You can decrease the centripetal acceleration by making the radius bigger. Okay? And so when you spin the pizza, right, when you give it a big angular acceleration and you increase the velocity of every point around the edge of your pizza, you are making it so it needs a lot of centripetal force or force directed towards the interior to keep it in that small circle. But the pizza dough doesn't have it, and so it stretches a little bit, okay? So you're stretching the pizza by spinning it, okay? This is the same concept as a centrifuge. If you ever take a biology class where you have to use a centrifuge, right? The same general idea. It's by spinning it, you create an incentive for it to move outwards, right? Okay, so this rotational bit comes in all over the place. And we use it all the time because it's really convenient. The nice thing about it, and the reason you do it on pizza dough, is because if you just lay the pizza dough out and try to smooth it out, right? you tend to have a hard time making a circle. But if you spin it, every point on the outside experiences the same radius and the same velocity, and so it gets the same force. So you expand the pizza circularly instead of expanding it in a straight line like you would with a rolling pin. Okay? So my point is simply that this shows up all over the place. And anytime, particularly in mechanical systems, where almost every engine ever invented involves spinning something, right? And then turning that spinning motion into something useful, like, say, the ability to drive in a straight line, or lift something, or spin your pizza dough. They're all involved in relating this rotational business over to linear business or translational business, tangential business. Okay, questions? Okay, we will call it then. Be sure to do the perusal reading for Wednesday's class. We're going to jump right in and start talking about torque on Wednesday. That is a concept that you will need to review. This whole rotation business drives me nuts because it's inherently three-dimensional, right? There's no way to do this in 2D. And yet we're going to try because that's all we have, right? Because we can't actually be in the same three-dimensional space. I actually briefly talked with somebody over in the computer science department about they have some virtual reality things that they do over there. It's not going to work for this semester, but it's just frustrating to me to try to do this the wrong way. Like, we know this is the wrong way to do it, and yet here we are. So be sure to do the reading. They have some good diagrams in the book that'll help you understand the directions of torques and these sorts of things. And we'll talk more about torque starting on Wednesday. Okay, I'll stick around. I'm going to stop the recording, but I will stick around and answer questions. If you have questions, stick around. If not, I will catch you on Wednesday.
Thank you.
Thanks.